Alright, we're going to start to talk about simple harmonic motion now. That was the big term we talked about a little bit earlier, and we're going to define simple harmonic motion. A lot of people think it's periodic motion. Not quite. We have to impose a few more conditions on it, but we will talk about that momentarily. Alright, so let's first of all look at this thing called the horizontal mass spring system. So what we're going to have is we're going to have this horizontal surface, we're going to have a spring, it's attached to a wall, and we're going to have a mass on there. Now, at the start, we're just going to have the mass at the equilibrium position, so x equals 0. So the spring here, it's neither stretched nor compressed. So if this system's at rest, the net force in the horizontal plane is 0. Nothing interesting is going to happen. We know by Newton's first law, if there is no net force acting on the object, it's going to continue to do what it's doing. So if it's at rest, it's going to continue being at rest. If it's in motion, it's going to continue to be in motion. So this system right now is not really interesting. What makes it a bit more interesting is if we start to displace this mass from equilibrium. It can be either compressed or we can stretch it out. It doesn't actually matter. So if we stretch this thing out, there is going to be a restoring force in the opposite direction. This is going to mean that there's a net force acting on the object and it's going to accelerate. Now the tricky part with this is because the acceleration is proportional to force by Newton's second law, and the force is going to change depending on the distance from equilibrium, we're going to have the acceleration changing as a function of time. This robs us of using any of our kinematics equations that we have derived up to this point because they all assume acceleration is constant. We will get around that though. We have some tricks up our sleeve. So any object that obeys Hooke's law and it continues to oscillate about a point. So like this mass, we pull it, it's going to kind of go back and forth and back and forth. We'd say it's oscillating about this point. So it's basically said to undergo what we call simple harmonic motion, or SHM. And then an object that undergoes SHM, the object is sometimes referred to as a simple harmonic oscillator. So for something to be in simple harmonic motion, first of all, we require the motion to be repetitive, so it has to be periodic. Now, this is where we impose a more strict condition. We need that the restoring force is directly proportional to the displacement from equilibrium. What we mean is we need that the relationship between force and displacement, it needs to be linear. And of course, we expect that force and the displacement to be in opposite directions. So mathematically, the condition that we're looking at is that we have the force is directly proportional to negative x. So this is a linear relationship. We'll come back to that technical point in a little bit, but that is really important. We want repetitive, predictable motion, and we want the force to be directly proportional to the displacement, or the negative of the displacement. So kind of here's what's going on when we look at the motion of a horizontal oscillator. So the first thing is, we're going to assume that we stretch this thing out to its maximum displacement from equilibrium. So that maximum displacement from equilibrium, we're going to give it a special name. We're going to refer to this as the amplitude, and we're going to denote that by A. So at this position here, we're going to be at the amplitude. So this distance here, we're going to call that A. So at this point, we haven't let it go yet, so it's not going to be moving, so speed 0. It's going to have maximum force because force is proportional to displacement. So maximum displacement, maximum force. And if it's at a maximum force, it's going to be at maximum acceleration. So when you let this thing go, it's really going to want to start flying. And of course, we have these negatives here because if we displace this right, which we've called positive, the force and acceleration have to go left. So we let this thing go. Now it's going to start to move towards the equilibrium. So once it gets to equilibrium, at this point, the force and acceleration are going to be 0 because it's at equilibrium and there's no stretching. But what we've done is we've taken all of that potential energy and we've converted it into kinetic energy. So at this point here, there is no potential energy, but there's maximum kinetic energy. So this object is traveling at its fastest speed. Now, since it's already in motion, by Newton's first law, since it's already in motion, it will continue to go in motion. So it's going to bypass the equilibrium, and then it's going to reach its maximum distance from equilibrium on the other side. So this is still going to be the amplitude, or rather the negative of the amplitude. So V is still going to be 0 at this point. Force and acceleration are going to be maxima in opposite directions. And then you're just going to have that motion repeat. We're going to go to the equilibrium, maximum kinetic energy at this point, no potential, force acceleration 0 at this point, V max. And then we're going to get back to the original position. So this whole A through E here, this represents a complete cycle. So this represents the oscillator doing a whole motion or a whole cycle. So we go from stretch to compression back to stretch. And the time it takes to do that, that's what we refer to as the period. Now for us in Physics 20, we're going to assume that that motion continues forever. So it's going to continue to oscillate about that equilibrium point forever and ever. Because we are going to ignore friction. Friction makes this a little bit more complicated, so we're going to ignore it for our purposes. Now what we could also do is, instead of having a horizontal system, we can absolutely have a vertical system. So generally what these look like, you have a spring. What we're going to do is we're going to attach something to it. So in this case, it looks like we have like a mass here. So what that's going to do is that is going to stretch out the spring, and it's going to stretch it out to this new equilibrium position. So this new equilibrium position, this is where the net force on this object is going to be 0, because that mass is going to have a force of gravity trying to pull it down, but where it's resting, that is going to be balanced out by the force of the spring acting on it, or that restoring force rather. Now, what we want to do here is we want to look at how this works in the context of simple harmonic motion. So the thing is, Hooke's law is still going to be valid in this situation. The only thing we have to be careful with is kind of looking at this whole net force. So when we're dealing with a spring and a mass spring system in the vertical plane, the forces we got to look at are Fg and the force of the spring, but the force of gravity is going to be constant, because we know that Fg is just mg. So if the mass isn't changing and the acceleration due to gravity isn't changing, Fg is not going to change. The only thing that will change is the force of the spring, or that restoring force, because it depends on that distance from equilibrium. So as it changes, the net force on this object is going to change. If the net force is changing, that means the acceleration is changing. Once again, that complicates things, but we will find a way around that. So we can kind of look here once again. So this is similar to the horizontal case, just now we're in the vertical. So at the very, you'll notice in all of these, Fg is constant because that mass is not changing. So at the maximum compression here, we have this spring force. It's smaller because we are not stretched nearly as much. Then we start to stretch this spring out more. Now it's going to have a larger spring force. We stretch it out more, an even larger spring force. So what's changing the net force, the acceleration on this object, is the changing spring force. So you'll also see here we have kind of our free body diagram, and we're showing the net force acting on this object. So the net force is changing. Here it's slightly down. Now at this equilibrium position we don't have any net force, and then the net force is going up, none, going down. The big thing you want to notice though is that the net force is always towards the equilibrium. So F net towards equilibrium. And this comes back to my point earlier. If you have anything that is a spring or an elastic, it doesn't want to be stretched or compressed. It wants to be in equilibrium. So the net force is always attempting to restore equilibrium. So if you're ever unsure of the direction, think about that. We always want to restore equilibrium. That is the goal here. So as we said, and again, this thing will continue forever if we're ignoring friction and air resistance. If you want it, and in reality, if you wanted to continue, you would need to have something that applies a force periodically. This is known as a driver. We'll talk about that a bit later. We're not going to do any math with it. It's more of a theory point. So we've already mentioned that simple harmonic motion, it is repetitive, it is predictable. So we're going to make the following statements. So we know that the restoring force is in the opposite direction of the displacement. We've talked about that quite a bit. So at the extremes of simple harmonic motion, so by that we're talking about at the amplitude. So the amplitude, the displacement is at maximum, and then at these points, force and acceleration are at their maximum. So F and A are at the max, velocity is going to be at 0. At equilibrium, force and acceleration are 0, and the velocity is going to be at its maximum. Those are the key points, and that's the thing that's going to save us a little bit. When we look at these oscillators, the only positions we're actually going to be looking at are the amplitudes and equilibrium. We are not going to look anywhere between them because it's a bit more complicated than we can deal with at the high school level. That would require us to deal with calculus, which we can't do right now. So we are going to limit the scope of our investigation. if you take any physics at the university level later, you will absolutely look at simple harmonic motion in a lot more depth, and it gets really hard. Right, so we got a spring. It's got a stiffness of 10 newtons per meter, and it's hung from a ceiling. So we've got a 2.5 kilogram mass. It's hung onto the spring, and it's going to reach a new equilibrium. So we want to find out how much this spring stretched when the mass was added. So here's kind of what's going on. So we have this lovely spring. You know, it's just kind of doing its thing. It's a really bad looking spring. And then eventually what's going to happen is we're going to hook a mass onto it, and it's going to stretch this thing out. What we would like to do is we'd like to find out how much did this actually stretch by with the addition of the mass. So at this point here, at equilibrium, we can draw a net force, we can draw a free body diagram. We are certainly going to have a force of gravity acting down, and we're going to have that restoring force of the spring. So I'm going to call it F spring. F spring is the same thing as restoring force, just that's the language I've decided to use. Now I also need some directions, so why don't I call down to be positive? So down's going to be positive. So the net force acting on this spring is going to be the force of gravity plus the force of the spring. Now this is in equilibrium. So equilibrium, as we talked about in dynamics, is a fancy way of saying net force is 0. And then we know Fg is just going to be mg. And then we know the force of the spring is going to be negative kx. So we would like to see how much we've stretched this. We are looking for the x value. So we have this plus negative, so I can bring this piece to the other side. So I'm going to have kx is equal to mg. So x is going to be this mg divided by k. I know the mass, I know the acceleration due to gravity, I know the spring constant. Let's solve for this thing. So the mass we're told is 2.5 kilograms. I've called down positive, so g is going to be positive 9.81 meters per second squared. And then k is not a, it's a vector, it's not a scalar. Oh my goodness, it's not a vector, it is a scalar. So we don't have to worry about direction. So let's have a look at this. So we have 2.5 times 9.81, and then we are going to divide that by 10. And we are going to get roughly 2.5 meters. Now, this came out as a positive number. Positive means down. What that's telling us is we've displaced this 2.5 meters down from where it started, which we expected. The spring started here. We put a mass that's going to pull it down. So the sign does make sense. So we're just going to say that the displacement of this spring is 2.5 meters, the downward direction. Now you might say, that's quite the stretch. Keep in mind, we're hanging a decent sized mass on it, and it's got a spring constant of 10 newtons per meter. It's actually a really, really weak spring, so it's going to be really easy to stretch. All right, let's look at the last question here. So I got a 0.250 kilogram mass. It's hung vertically from a spring such that the mass spring system has a natural length of 35 centimeters relative to where the spring is fixed. So the mass spring system is stretched and released when the length of the mass spring system is 52 centimeters relative to where the spring is fixed. Its acceleration is 0.450 meters per second squared up. Determine the spring constant. Okay, there is a lot going on here. So here's kind of what we're told. We're told that this spring, it's hung, so kind of its equilibrium position. So this is equilibrium. What we've been told is that this has a natural length of 35 centimeters. Now, later we stretched this thing out and let it go. Now, what we've been told is that at some point later, when this thing happens to have, the whole system happens to have a length of 52 centimeters, we're told that the acceleration is going to be up, and we're told it has an acceleration of 0.450 meters per second squared. What we've been asked to do with this information is we've been asked to determine the spring constant. So there is a lot going on. The first big trap, though, is we're given these two distances. Remember that we want the distance from equilibrium. So this is my equilibrium position here. what I want is I want this actual distance here. So I want to know how much this is stretched. It has a natural length of 35 centimeters. It's stretched to 52 centimeters. So the actual distance from equilibrium, so we're going to take off that 52 and 35. So this is going to give us 17 centimeters, or 0.170 meters. What this is trying to tell us is that we have stretched this spring from equilibrium by 17 centimeters. That's really important. Now, let's draw a free body diagram for this object. So my free body diagram, so my FBD. Now I'm going to have a force of gravity trying to pull this thing down. So I have my FG. Now because this thing is accelerating up, that is telling us the net force is also going to be upwards. So we need to have that restoring force on the spring, or the force of the spring. It's got to be greater than the force of gravity such that our net force is going up. So for this, let's call up to be positive. So the net force acting on our system here, it's going to be the force of the spring plus the force of gravity. And then we know we have MA equals negative KX. So we can't forget that negative because we're dealing with the spring, plus mg. So my goal here is to find K. So I'm going to have to do a little bit of rearrangement. First of all, let's bring this to the other side. So I'm going to have MA plus KX equals mg. And then we'll take that MA term, put it to the other side. So we're going to get KX equals to mg minus MA. And then, of course, we're going to divide this lastly by this x value. The hard part with this, G, A, and X, they're all vectors. What that means is you have to be incredibly careful with the sign conventions. So if you're careful with the sign conventions, you should be fine. So we have a mass. We're told it is 0.250 kilograms. So G is directed down, but I have called up to be positive, so I have to put in negative 9.81 meters per second squared. And then from that, we are going to subtract 0.250 kilograms. The acceleration is directed up. We have called that positive. That's fine. So we're going to put 0.450 meters per second squared. And then lastly, the displacement from equilibrium is also a vector. We have stretched this thing downwards. So because we've stretched this thing downwards, we actually have to put this in as negative 0.170 meters. That's really important. If we forget that, we're going to get a K value that's negative, which doesn't make any sense. So lastly, let's look at what we got here. So we got this negative 9.81, we got that minus 0.450, so we got that divided by negative 0.17. So what we're going to get is we're going to get about 15.1 newtons per meter. So that's going to be the spring constant for this spring. So this is a dynamics question with springs in it. The main thing that you have to watch out for is watch out for your vectors and your directions. If you're really careful with those, you'll get the question right. But that's the message I've tried to give you all along. Anything with vectors, be really careful with direction.